the last part of this presentation, which is not very fundamental stuff, but just one slide that I want to show. Again, given that we have so many Fortran programmers here, just to give you a feeling of how Fortran looks like, for instance, in PGI's CUDA Fortran. As I said, the one approach is the mixed language approach. So basically, on the Fortran side, you have a call my func. Oh, and there's a C missing. Call my func, and then you have an extern C function that then launches the kernel. So that's one approach. The upside is it works with any compiler, fairly straightforward. The only problem is that you have to worry about the calling conventions. That's whether you need to underscore the function name or not when you call C from the Fortran side. And you have to worry about two different languages, so that can be a bit inconvenient. Now with PGI's CUDA Fortran, you have extensions to Fortran that, for instance, if you have an array U that has a certain dimension, you can create arrays that have the attribute device that will live on the GPU. And so simply by assigning U to A, you're copying data between host and GPU. You have a mechanism for calling kernels, so CUDA Fortran also supports the triple chevron notation. So otherwise, those are simple functions with now an attribute called global that it identifies these subroutines as kernels. So this is not meant to be an example. It just should give you a bit of flavor, a feeling for how it looks like to write CUDA Fortran code. The upside is definitely that you have a very Fortran-like approach to CUDA. The downside is that it's currently only supported by PGI. But PGI's compiler is available on TODI, so you can give it a try there if you just want to play around with some examples. Okay, so what I didn't talk about this morning was anything about optimization. And frankly, there's a lot of talks out online about doing optimizations in general, CUDA optimizations. There is lots of material. Please just go out and Google for whatever, CUDA optimization, and you will find various presentations. I also didn't talk about streams in very much detail, so we'll come back to that. And the multi-GPU programming is another thing that I simply ignored so far. Okay, now coming to this afternoon's topic, which is CUDA5 and Kepler. So first, I want to talk a bit about Kepler itself, what the chip does, and what the design decisions were behind it. And then later on come to some of the new features that are supported by CUDA5. For those of you who knew TODI before it became an XK7, while it was still an XK6, at that point it had a Fermi-based GPU, which is just the generation before Kepler. Kepler devices became available early 2012, and the GK110 became available in the second half of 2012. The goal was to provide a step up in terms of performance from the previous generation, to also make it much more energy efficient. So basically, increasing performance and drawing more power, that's quote unquote easy. But improving performance without requiring more power, that's much more difficult. And that was the goal of the Kepler device. And the last focus was on programmability, so to make life easier for developers to get to a good utilization of the device. So we come back to the famous GK110 block diagram with the 15 streaming multiprocessors. And here's the subtle difference, right? GK110, that's the name of the chip that sits on the GPU. And that's the chip that's a whole family of different products. And the K20X, the GPU that you have in CUDA, is one product that has a GK110 chip. Now, the different products that are being produced with this one chip differ in the number of streaming multiprocessors that you have. So while a GK110 chip can have up to 15 streaming multiprocessors, the products that are being sold have either 14 or 13 or even fewer streaming multiprocessors. So that's where the whole confusion came about, how many SMs that there are. On a GK110 chip, in theory, you can have up to 15 streaming multiprocessors. Technicality, and given that you're not buying the machine, but it's already there, it doesn't really matter. But it's, yeah, just wanted to mention that. So yeah, we have up to 15 streaming multiprocessors. Each one of those chips can, in theory, deliver more than a teraflop of floating point, double precision floating point performance. Has a sizable cache that's twice as large as the one that we had on the Fermi chip, and has a 384-bit GDDR5 interface to the memory on the device. I'm not particularly keen on all these technical numbers, but some of these numbers can be useful to just have somewhere sitting around for reference if you're doing a theoretical performance analysis of a kernel. Right? If you know that your kernel doesn't do anything else than read in data from GPU memory onto the streaming multiprocessors and writing it back out, you should be able to at least get close to the theoretical bandwidth that you could have on this device. And you can infer that from the width of your bus, the clock of your memory system, and that's another one of those numbers that you can determine based on the either look up in the specs or determined by some figures that are reported by tools that are available on CUDA. So that's a weak but somewhat of a justification for showing you these numbers. Anyway, comparing the Kepler streaming multiprocessor to the Fermi streaming multiprocessor shows that what happened between these two generations is that the amount of parallelism has increased again quite dramatically. So we have many more of the floating point units that sit on each one of these processors. We have more double precision units, and they have introduced new instructions that can help you get more performance out of the chip. A bit in more detail, what has changed? So we have more floating point units that can lead to a higher throughput of floating point instructions. But that's not all. We can also have more CUDA blocks per SM. On Fermi, it was up to 8 blocks. On Kepler, we can have up to 16 blocks that can sit on the same SM. Now, if you remember the previous presentation, having more blocks that are sitting on an SM allows you to better hide the access latency, for instance, for global memory accesses. So with more blocks being able to be resident on a streaming multiprocessor, this can potentially help you get better, finally get better performance, get better utilization of your chip. Yes?
Because the router is
Coming and going, yeah.
Sorry.
I want to have one of those Britney Spears head things. Right. And so what you can see is that a lot of the other resources, many of those increase by a factor of 2. Particularly interesting for a lot of applications is the size of the register file. So you have twice as many registers that are available that can also help you to finally to improve the performance of your kernels. And then finally, you have the amount of shared memory that has remained the same. Now, this may seem like a limitation, but there is actually some changes in the architecture that help you avoid use of shared memory that you had in previous cases, and I'll come back to that in a second. So what this shows is that instead of just saying, okay, let's double the number of floating point units that we have on this chip, we went through all the kind of analysis of the different workloads that are used on GPUs. And it was based on these analyses, it was decided to increase the different types of resources on a case-by-case basis. So some of the changes with Kepler. With Fermi, you had a certain number of registers available, 32,000 altogether. And when you do the math, when you think about how many blocks and how many threads you could have theoretically resident on a streaming multiprocessor, it turns out that you can use something like 21 or so registers per thread maximum. Now, if you were not fully using the streaming multiprocessor, so if you had fewer resident threads than potentially could go there, you could increase the register use of a thread up to 63 registers. But there was no way that any thread could have more than 63 registers, simply because the width of the address for addressing registers in the instructions was too short, only had whatever, 63, that's 8 bits, available to address that. 6 bits. And so one of the changes now with Fermi is that we can actually use all the way up to 255 registers per thread. Now, if you're using 255 registers per thread, you're not going to get as many blocks on the SM as you could. If you want to have so-called full occupancy, so if you want to have as many threads resident on an SM as you can, you're still limited to 31 registers. But that's already a step up. That's almost 50% more than you had before. So when you have a kernel that is occupancy limited, on Kepler, there's a certain chance that you get your occupancy higher now. Or if you had a kernel that had to spill a lot of registers, that again should no longer be the case. Right? Just if you think of it in right, all the registers on Kepler or on previous generations are 32 bits wide. So if you have double precision code, and especially when you have double precision complex numbers, that already uses 4 registers for one number. So it's fairly easy to use up a lot of registers in your kernels. And so having access to more of them can be a very good a way of avoiding to move data between global memory and the streaming multiprocessor. Then there was a whole range of additional instructions. Actually, one entirely new instruction that was added, the so-called intra-warp data exchange or intra-warp shuffle instruction. Then the atomic operations saw a significant redesign and significant performance improvement. And then there's some other operations, other instructions that are mainly useful to the compiler, so not to the end user, but it also helps the compiler to create better code. So we will go through these 3 groups in the following. So the first one, and somewhat most exciting one, is the intra-warp shuffle instruction. So if this morning was the first time that you heard about CUDA, then that's probably a bit confusing. But remember, if you wanted to have threads within a block communicate with each other, the only way in previous generation GPUs was to move data to shared memory. So one thread moves it to shared memory, and the other thread reads it out of shared memory. So you always had to go through shared memory for this exchange. Now, the problem with that is that you need to allocate this shared memory. So even if you're within your kernel, you can reuse some of the shared memory as time goes on. You still have to allocate a buffer for that. And as we saw, shared memory is limited and therefore a scarce resource. What Shuffle allows you now is that within a bundle of these threads within a warp, you can now grab data from any one of your neighboring threads or from any thread in the same warp. So there's basically 3 different forms of Shuffle. One says that each thread can just say, I want to get the data from thread whatever, 5. Thread 1 says, I want to get data from thread 5. Thread 2 says, I want to get my data from thread 7, and so on. So arbitrary indexed pattern. Then there's 2 for shifting operations. So if you need to do exchange data with your nearest neighbors. And then you have a butterfly exchange that can be particularly helpful in cases like FFTs, where you have these butterfly reductions, and you need to grab data from further and further away elements. So, right. One standard example, especially when you go and search for CUDA optimization presentations, is this example where you do a parallel prefix-sum. So a parallel prefix-sum is the algorithm that takes an array of a certain number of elements, and you're computing the array that contains the sum of the elements up down here, the sum of the elements up to this element. So you have 3, then you have 3 plus 8 is 11, 3 plus 8 plus 2 is 13, and so on. And so you can do a lot of cool operations with this parallel prefix-sum. Now, the way that you usually do it in CUDA, in the old implementations, was that you had this array in shared memory, and then each thread goes out and grabs his 1 up element and adds it to himself, and then you go up and grab the 2 up element, or sorry, 3 up element, and then the 4 up elements, and you add them together. With Shuffle, you don't need to do that. You don't need the round trip anymore. You can just say, I want the value from 1 element up, or I want the value of 2 elements up, and so on. So that's a cool thing to do. For instance, we have this one case of a code that needs to do a lot of small matrix products, up to or down to something like 5 by 5 elements. And for that one, we can do this entirely with these products within a single warp, right? Because the 5 by 5 element matrix has 25 elements, so that's less than the 32 elements that you have in a warp. And so for that, the entire matrix product can be done exclusively with warp shuffles. So it's one of these instructions where, yeah, when you write the kernel and you see that you're running out of shared memory, think if there's a way of using a warp shuffle instruction. Yes?
How do you use the instructions?
It's shown exactly here. So here it's __ shuffle up, and then you have a value. So let's see, right? So yeah, it's an intrinsic. And you know, we had recently a philosophical discussion about what we like about the CUDA model and what not. And I mean, it is to some degree way too low level for something that you want to worry about. That's also why it's prefixed with an underscore. It's kind of a hardcore optimization option, but it is actually very helpful simply because it allows you to bypass this resource limit that you have otherwise, which is the amount of shared memory. So yeah, it's not, you probably shouldn't start designing a kernel by saying, okay, I want to use my shuffle instruction. It should be a consideration that you do way, way down the road. Okay, atomic instructions. I didn't mention atomics this morning, so just very briefly, right? The GPU is a very massively parallel system, and you have multiple streaming multiprocessors that might be working on the same data element in global memory. So if you are not careful, it could happen that you're creating a race condition because multiple threads try to update the same value in global memory. Atomic instructions are a safe way, a mechanism to allow you to avoid this race condition. Now, the very early CUDA programmable GPUs didn't even have atomics. So you had to write your algorithm in a way to avoid atomics. Then later on, generations offered atomics, but the performance of it was very poor. And that, yeah, you could only use it kind of as a last resort if it was really too hard to write your algorithm in a way that you would avoid atomic updates in global memory. With Kepler, atomics are actually so fast that they are, in many cases, only slightly slower than global memory accesses. And you have a whole range of operations on both 32 and 64-bit values. So that's doing actual arithmetic, adding, and then compare and swapping. So that's useful for creating locks in global memory, exchanges, and then minning and maxing. So yeah, the atomics now become a true mechanism for designing your kernels, and it shouldn't be just used as an excuse for not having to think. Again, an example is here. If you had an array and you wanted to compute the sum of all the elements in this array, what you would do in previous generations is you would take your long array, break it up into chunks, and each one of these sections would be processed by one of the streaming multiprocessors. Given that there is no way of communicating between the streaming multiprocessors, each one would write his own partial sum out to global memory. And then you would have to launch a new kernel that would reduce all these partial sums into the final result. With atomics, you can save yourself this two-step process. And basically, each thread block computes its local partial sum and then does an atomic update in global memory. And given that this is atomic, you know that so if this thread block has computed his partial sum, and he does an atomic update, he will know that during the time after he read the value from global memory, added his partial sum, and wrote it back out, that in this whole process, there was no other thread that was messing around with the value in global memory. So again, that's one of those programmability features that helps you just write code without a lot of complications to avoid these type of race conditions. An example here is that there's a code, SPECFEM, which is a spectral element code. And the authors spent a lot of time and effort in, so the one problem with spectral element codes is that you have nodes that are sitting on adjacent, or that are shared between multiple elements. And so you have this problem that you might update nodes from the different elements concurrently. And so in order to avoid these race conditions, the authors went through lengths of coming up with a mesh coloring scheme that would avoid that you have ever the situation of touching the same nodes concurrently and so on. And it actually helped very much on Fermi. But with Kepler, all this effort is basically gone. They can now just use atomic updates in global memory, and they get good performance. So again, it can help you save a lot of effort by just using atomics. Yes?
I guess if there is a limit in the number of elements that you want to sum up in this case, like you want to, because if you're using atomics, you are anyway serializing like sum. So I guess there is a limit in which this technique works, and now that you have to go back to
Right, absolutely, absolutely. So I mean, one thing to keep in mind is, yeah, I mean, with with many of these statements, one has to be a bit careful because it's really dependent on the exact context under which this happens. In case of the atomics, one of the big questions is how many concurrent accesses do you actually have on the same variable, right? So, and yeah, with another code, we have this issue that for guaranteeing correctness, we need to do an atomic update. But probability that you have a conflict is very slim. And so in that case, it's actually affordable to do it at the very fine granularity to use atomic updates, simply because you're not locking out everybody else at that point. The other threads still can do their job. They still can do their atomic updates on different parts of the memory. But yes, if you have a lot of contention, right? If there was thousands of blocks and they all had exactly the same number of operations, so you could assume that they would very closely to each other finish their local computation and they would all hit the same one variable in global memory at the same time. There you probably want to make sure that you have a fair amount of work that happens on a per block basis, just to relax a bit the number of contentions that you have on this one variable. So yeah, it's a trade-off again. Yeah. Okay, another one, another change that was made with Kepler is related to textures. So one is that the performance of textures got significantly improved. Now, one thing that people tend to forget in the HPC community is that GPUs come out of the graphical side. So there's a lot of hardware available that is concentrating on graphics features, one of them being textures. Now, what textures are again, on the graphic side, is basically you have a triangle and you want to put a certain texture onto this triangle. And so what this feature does is it allows you to do automatic interpolation between adjacent values. It has additional caches when coming from global memory to make sure that you have good performance for accessing elements that are not nicely aligned with each other. So yeah, there's all these hardware. However, using this hardware in previous versions of GPUs was sometimes a bit painful. And depending on the application, it was also not, it couldn't be as fast as accessing global memory. Now, what changed with the SMX is that we have not only faster texture operations, but we also have more texture cache. But the really cool feature is now that we have an additional data path from global memory that sits below L2 cache through the texture cache into the streaming multiprocessors. So previously, we had to go through this texturing hardware, which is a bit painful to set up. So you had to have a bunch of function calls to just set up the textures. You had to bind them, and you had to use a separate call to access the elements in there. There is now a separate data path that basically says, load me this value through the texture cache into my streaming multiprocessor. There is a way of accessing this instruction directly. It's called LDG, and it's another one of those fairly low-level instructions. That's why it has a double underscore prefix. But in theory, the compiler should be smart enough to detect accesses that could go through this data path by itself. The way to do that is to label variables with the qualifiers const and restrict. Why is that? So textures are fed through a read-only cache. Right? They're a pure read-only mechanism. And so if you're telling the compiler that you have a variable, an array, that is guaranteed to be only read, and if you guarantee to the compiler that there is no other pointer that could possibly modify the data that you're trying to read, then it's safe enough for the compiler to say, I might not need to go through the usual data path, which goes from from L2 through L1 into the streaming multiprocessor, but to actually get it through the texture pipe. So as a programmer, what that means to you is that just make sure that you're labeling your variables with const restrict when you can do it. So for instance, here we have a SAXP. So it's a scalar stretching of a vector. And what you add to your standard signature is just the constant, the restrict modifier to your input variable, and it will tell the compiler to use the LDG instruction to load data. So other kind of cool features, yeah, we have a more efficient memory controller. That means we have higher bandwidth to global memory. We have more L2 cache, so chances are higher that you will find your data actually in the L2 cache. But keep in mind, caches, again, it's not like on a CPU where you're doing a cache blocking to make sure that your data sits in cache. Because you have so many threads that are accessing data in a very unpredictable manner that it's very hard to write a code with these caches in mind. But the goal is that that the hardware will provide you a mechanism to quicker access data than you would have to, than if you would have to go all the way out to global memory. And then the last one is that error correction. One of the features that you have on the Tesla devices, as we have in Kepler, is error correcting memory. So it's capable of detecting bit errors and correcting them. The performance of that one has been increased quite dramatically. Now, if you have a Fermi code, what do you need to do? In theory, as long as you embed the so-called PTX code in your GPU code, it will just run on Kepler. So there's nothing you need to do. In order to get somewhat better results, you certainly want to recompile. And given that there is now some small changes on the surface, but actually fundamental differences, like the warp shuffle instruction, that's something that you as a programmer have to take advantage of it. So it might make sense to go back to the kernels that you have, the ones that you really care about the performance, and tune them for Kepler. But again, that's not something that you want to do for every single kernel. It's for the ones that you really care about. So now, one thing with Kepler is that, as I said, the amount of parallelism that the device offers has been significantly increased. Oops. And so it becomes challenging in many cases that an application by itself can take advantage of all of the full device. And so one of the focuses of Kepler was to make sure that there's good mechanisms of having multiple grids that run concurrently on the same device at the same time. So I come back a bit to the concept of streams. Right? when you have your host application and it launches a bunch of kernels, if they're in the same stream, they will be moved, they will be put onto the streaming multiprocessors in order. And then if you have like the grade 1, 2, and 3, and so on, they will be in order dispatched to the SM. So the grade 1 will be put on the SM. And then whatever, SM0 will finish first, because for whatever reason, the kernels that you had that were dispatched to this streaming multiprocessor finished first. Well, now you create a big load imbalance, and that means you have wasted resources here. This guy is just sitting idle and waiting for the other grid to finish. Now, if you have a second stream, and you had the same situation, so you had, again, grid 1 that fills the entire GPU. And then the kernels on the streaming multiprocessor 0 had completed. Well, the grid management unit knows that from the first stream, it cannot start executing kernels, because that's part of the programming model, that one kernel only starts after the previous one has completed, if those kernel launches are in the same stream. But there's no guarantee of an order of kernel launches that are placed in different streams. And so the grid management unit now has the freedom of starting grade 5, which comes in from a different stream, on streaming multiprocessor 0, and continue to work on those. So this helps to better utilize the entire device, which is particularly useful if you have a lot of small kernels that operate on, or kernels that operate on relatively small grids. So in that case, it might be useful to use multiple streams. Another example is for using streams are asynchronous data transfers. And I think we heard that this morning already from Alistair. So basically, right, if you would have just synchronous transfers, and we have some work on the CPU that then hands off data to the GPU, so it's taking a certain amount of time to migrate data to the GPU. The GPU then processes all this data, and it takes a certain amount of time until the result comes back to the CPU. Well, with asynchronous transfers, so with the ability of moving data while you're processing data on the GPU, you can significantly cut down the overall time spent between start of the operation and finish. And the way to do that is to use the asynchronous memory transfer function. So instead of CUDA memcopy, it's now CUDA memcopy async, which is exactly the same as CUDA memcopy. It only, as an additional parameter, takes this stream ID. And the other thing is that in the kernel launches, as we learned this morning, you now have to provide the stream ID as well. Now, some of you might say, well, that has been advertised for Fermi as well. Weren't we able to launch grids concurrently on Fermi? And that's true. Fermi did allow you to do that. But there's some technical challenges that made it very hard to get the desired effect. Basically, what Fermi allowed you was to have a 16-way concurrency, so you could have up to 16 streams. And those streams would then feed the kernel launches in these individual streams onto the hardware work queue. And then you had a dispatch unit here on the side that was looking at the hardware work queue and said, oh, I have a streaming multiprocessor that's currently idle, not doing anything. I'll take the next available kernel here and put it onto that resource. Now, given that there was only a single hardware queue, it was hard to get good overlap because, well, there was only limited situations where you could see kernel launches from one queue, from one stream, and kernel launches from another stream that were available. So only at the tape out of A, B, and C, it would see, oh, I can now start launching the P kernel. So you had a lot of these so-called false dependencies, where in theory, after A, or while A was working, it could already have started with P. But the unit that was scheduling the work didn't have access to P. It didn't see that there was something coming down the road that could be done concurrently. With Kepler, this has improved dramatically because now there's not only a single work queue, but there's multiple work queues. So the unit that sits over here and then finally dispatches the work can make the best possible decision at any given time for the available resources. It can see, oh, my A is now, in order to start B, I still have to wait for a few more blocks that are part of kernel A. But I can start with P now. And so this feature helps you to better utilize, again, the overall GPU. And just as a how this was accomplished, just a different way of looking at the problem. Here we had these different queues that were all, the different streams that were all put into a single work queue that then was dispatched out to the individual streaming multiprocessors. That's the Fermi world. And now with Kepler, we have this additional grid management unit in between that A can select better from the different streams to place the next kernel. And another cool feature is this line that goes back, and we will come back to that later. But that's, that enables a whole lot of additional cool applications. Now, the fact that we have these multiple work queues is called hyperqueue. And it just enables more efficient scheduling, and especially in case of MPI applications, that can have a dramatic impact. Right, so if you imagine that you have a single thread that tries to work with multiple streams, and in the Fermi picture, right, where you very carefully have to schedule what kernel is being launched at what point so that you get good overlap of the execution. Well, you can possibly do that, and people have, with heroic efforts, have managed to do good, to get good overlap of kernel launches. But if you're now saying that it's not within a single application, but if you want to have multiple CPU processes that all share the same GPU, that all launch work on the GPU, well, that's pretty much impossible to get this good scheduling and this tight scheduling to make sure that you have a good, no false dependencies. And so with hyperqueue, so this situation, it would, for instance, happen when you want to share a GPU amongst multiple MPI ranks. And with hyperqueue, this should help now in the situations where you share a GPU amongst multiple MPI ranks. So let's look at this scaling example of an MPI application. So if we have a multi-core CPU system, and we have this amount of time on a single core, the light green part is the part of the application that could potentially benefit from the GPU. And then we have the part that is CPU parallelizable, but doesn't run on the GPU. And then we just have some serial part that simply cannot be scaled. Well, if we use 2 cores, both the part that could potentially parallelize on the GPU certainly will also parallelize on the CPU. And the CPU parallelizable part, they simply will be cut in half. And if we go to 4, and if we go to 8, that's the picture we're going to see. The serial part will remain the same. The other ones will be proportionally reduced. Now, if you can only use a single MPI rank that touches this GPU, well, it will affect the GPU parallelizable part. And it will cut that down to a very small amount of time. But it will not affect the CPU parallelizable part, because it will be exactly, the amount of CPU parallelizable work will be exactly the same as if you had just a single core. So the best speed up in this case that you could see from adding a GPU to this system would be probably comparable to 2 cores. But it wouldn't, with just using 4 CPU cores, would already beat you in this situation. Now with Hypercube, and with the ability of being able to share the GPU amongst multiple MPI ranks, we will still see the same speed up on the CPU-only part that we had with the pure CPU implementation. But on top of that, we also get the acceleration of the GPU part. And so this allows us to nicely outperform the GPU, the CPU only altogether. Now, what type of applications are very suitable for seeing a benefit from proxy? And I think I might even have a picture here. Right. So this was for a code CP2K. That's a code that still does a fair amount of work on the CPU. And actually, if I come back here, if you think about it, what codes benefit the most? It's the ones that still have a fairly sizable dark green component. Because if the dark green component was nil, well, then yeah, you would just see the benefit on a single. The overall time would still just be this amount, and so you would be faster with a single GPU on a single MPI rank per node. You would be faster than doing the work on 8 CPU cores. So it's interesting for applications that still have a fair amount of work on the CPU. And it's also interesting, I mean, that can be by design, that a certain application simply isn't suitable for GPU acceleration in some part. Or alternatively, it's in these cases where you're in the process of moving an application to GPUs, right? When you are moving your code to GPUs, well, you start somewhere. You start with the most expensive kernel. Well, you might be able to accelerate that one very dramatically, but if that means that you can now use only a single CPU core, it might be that your overall speed up will be completely annihilated. But with Hypercube, you then can use all the still use the same amount of concurrency that you had on the core before. So bottom line from this is that if you have a code, if you're in the process of moving a code to GPUs, or if you have a code that has a fair amount of CPU work, then you might be interested in looking into Hypercube. And so the coolest thing about all that is, even though technically it has to do with the fact that you're now using multiple streams to dispatch the work to the GPU, and it's all being handled nicely by the hardware, all you have to do on a Cray system is to set the environment variable Cray CUDA proxy to 1. And it will allow you to use multiple MPI ranks on a single node and to let those multiple MPI ranks share the GPU. So we can do as one of the, I'll continue a little bit, but as one of the samples, you can use the code that Alistair has shown you this morning, the MPI code, and we can run it on under proxy on 30. Okay, now having said all that, one thing to keep in mind is that, right, you're optimizing with GPUs, you're optimizing the single MPI rank part of your code. Never forget that there is also a whole lot of other parts of your code. This one here is from, I forgot what it was, but a profile on a close to 400 rank code. And the blue part is the actual compute part. Well, if we accelerate, and the rest is messaging and waiting and whatnot. If we accelerate the compute part with the GPUs, it simply means that those parts become much more expensive. So first action item should always be make sure that the messaging is as optimal as possible. Oops. Now, I mentioned before the cool feature, which is this arrow back here that goes from the streamy multiprocessors to the grid management unit. There was another thing that came out in this analysis of the different workloads that were used on Fermi GPUs. And there was just a set of applications that were very hard to get good performance on with GPUs. One thing was that there was no way of making library calls from kernels. And it's always hard to make sure what part needs to be on the CPU and what part needs to be on the GPU. Then we had the issues of backfilling the GPU. And as I said, with HyperQ, that's one way of addressing that. And then there was all the things about data-dependent execution, like tree traversals so recursive algorithms in particular, or if you had to make certain decisions based on a data value. In previous, so all that was addressed with the feature called dynamic parallelism. What does dynamic parallelism mean? It's basically just that the GPU can now create work for itself. It can launch new grids on the GPU. So for instance, in the previous picture, the way that CUDA is usually taught, it's you're on the CPU and you launch a kernel. The kernel executes and it's asynchronous, all fine, but eventually you get a result back from the GPU and you launch based on this result, you launch the next kernel. In this case, we now launch 4 kernels and the result comes back and then, so the CPU is in charge, the GPU is a coprocessor. Now, with dynamic parallelism, what you can do is that the CPU kicks off the GPU and the kernels then make themselves a decision that they want to create more work. And so they can spawn more work, and these kernels themselves can spawn more work, and you never have to go back to the CPU and ask, what should I do next? So it saves you a lot of these round trips to the CPU, and it can also help you make an algorithm more, to express the algorithm more naturally than without it. One typical example for this type of applications would be some type of mesh refinement, right? You know that you have a certain resolution of your computational mesh, and you see that there are some features that need to be resolved that you cannot resolve at the moment with your mesh. Well, with a statically decomposed mesh, you would have to calculate with the worst case scenario. So you would just completely over-resolve some of the areas that are way outside of the area of interest. Now, there is people who actually manage to do adaptive meshes with the old way of writing CUDA applications, so with a pure coprocessor model. But it can be very challenging to express that efficiently. With dynamic parallelism, you can now make these decisions about local refinement straight on the GPU within an individual block. Yeah, that's just another example. For instance, for an LU decomposition. And if you want to have multiple LU decompositions that are being performed on the GPU, what you would have to do in the old model is that after each one, you would have to go back to the CPU and say, well, what's my next blast call that I need to call? And then what's the next one, and so on. With dynamic parallelism, these decisions can now be made within the same thread block. So it's not necessarily a mechanism for achieving much higher performance, but it's a mechanism of expressing algorithms in a more natural form. So how does that look in practice? So here we have a very basic example, and that's actually one of the samples that's also on 30, and we will look at that afterwards, but let's just have a look at it here. So we have the main program, runs on the CPU. We launch the parent kernel, and we just use a single thread and a single block. And then we have a device synchronized and we finish. Now the parent kernel is a typical kernel as you have it with the global modifier. But then inside this kernel, we have another kernel launch. And this kernel launch now calls the child kernel, and the child kernel, well, writes out some message. Here you can actually see a function call, in this case printf, from within a kernel. So again, if you haven't heard about CUDA before, or if you haven't looked at CUDA before, then this seems like, well, what's the big deal? If you've done CUDA before, then you knew that this was a complete no-no. So there is no kernel launches within a kernel. There was the possibility of calling printf. That's a simplified version. But this could be an arbitrary function call here. There was also a complete no-no. There was no function calls from within kernels. The way to enable this dynamic parallelism is to set an additional NVCC flag, and that's called RDC, which is relocatable device code, to true. And then you get all these features. Given that we're using printf here, we also need to link against the runtime library. Oh, sorry, not the printf, but the device synchronize function here, another function that is being called. Given that we call device synchronize from within the parent kernel, requires that we load a special form of the runtime library. So we need to load the CUDA def RT library as well. But let's look at this in practice. Vim was finished. So we have sample 5. Which is exactly the same as, sample 4, sorry. So it's a tiny modification of the code I showed you. Here the child kernel takes an additional parameter and then prints out its own ID and the parent ID. And the parent passes in its own thread ID to the kernel. So we are launching the parent kernel with 5 threads. And each thread launches its new grid of the child kernel with 3 threads, and it passes his own ID in as an argument. So we should get 5 times 3 hello kid messages with the D running from 0 to 2 and the parent running from 0 to 4. And this is a bit painful. Okay, so here you can see the command line that was used. Again, we compile for SM35, so for the Kepler devices, for the K20X. We have the RDC, the relocatable device code flag set to true, and we link in the device version of the runtime library. Then we need to get the an allocation. Well, if you have a less painful connection than I do. Oops, no. So. Then there is a certain hope that we get the result at one point. Yes, and so here it executed. So this should be 15, and we have the kids going from 1 to 2, and the parents going from 0 to 2, and the parents going from 0 to 4. So this is a very simple example of using CUDA dynamic parallelism. It is a new feature. It's still, we're interested in hearing about what type of applications work well with this feature, whether it made your life easier or what changes that you would like to see. It's one of those features where in the current implementation in CUDA5, there's actually a few limitations that are still there, right? As you saw, we can now launch grids from within each individual thread. So you can very quickly create a huge amount of threads that are being executed, this huge avalanche. And so you probably will hardly ever see a CUDA dynamic parallelism program where a kernel just blankly says, launch this new grid. But usually the pattern you would see is that thread 0 of a block will launch a new grid, or that there's some other form of limiting mechanism to avoid that you're creating way too much work. Also, as you can imagine, somewhere you need to store the state of the individual SMs, so it uses quite a bit of memory. Right? Just imagine, I mean, each SM, in theory, can have up to 28,000 threads. Each of those 28,000 threads has a certain amount of registers that they need to keep track of, and so on. All this state needs to be saved before you then go on and compute or launch next grid. So, yeah, it's fairly resource intensive. But again, the goal is not to have a very lightweight mechanism, but the goal is to make programming easier. And so if you have an application that requires a lot of like tree traversals, for instance, it would be very interesting to see how CDP, CUDA dynamic parallelism, can help you to express the parallelism in your application. Okay. Now, my favorite confusogram, which is the CUDA compile trajectory. I think I've used the word PTX before, and so there's sometimes a bit of confusion of what is what, right? If you compile a CUDA program, it creates a binary, yes, but there is talk about there's the CU files, the PTX files, the CUBIN files, SAS, and so on. So what I'm trying to do in the following is just to hopefully straighten this out a little bit. So when you have your source code, your test.cu file, well, what the compiler will do is, in a first pass, it will split this test.cu program into the host and device code. And the host code will actually be handed off to the host system compiler, so GCC on the GCC on the Linux-based system, or on Windows side it can be the Microsoft compiler. But the other part, and so the host code is just being compiled into a host object code that eventually needs to be linked against the host side libraries, and it produces an a.out, the binary. Now the device code can be compiled into PTX. PTX is something like an virtual assembly language for the GPU. So it is basically assembly language, but it's not machine language of one particular GPU, but it's an abstract machine language. And so if you're saying, I'm targeting a GPU from 3 years ago, or I'm targeting a Fermi or a Kepler GPU, well, they have different instruction sets. And so there's an additional step involved that takes the PTX code and translates it into the so-called CUBIN code, which is the code, the binary code for one particular architecture. So that's what you're selecting with SM35, architecture equals SM35. That basically says it should create binary code for the SM35 architecture. Now this CUBIN code, it's basically from the host perspective, it's just a piece of text. It cannot do anything with it. So before CUDA5, what happened was that this CUBIN code was embedded into the object file, and it was linked into the a.out, all fine and good, but the linker here didn't have any insight into this GPU code. It just said, oh, I'm getting this additional piece of data, this additional piece of text. I don't know what to do. I treat it as text, and finally the GPU can do something with it. Creating code for one particular architecture is actually an optional thing. You can just include the PTX code into your binary, and then leave it to the driver, the GPU driver, that will, on the fly, translate this PTX code into the binaries for your given hardware. That's a very clever mechanism that guarantees you future compatibility. So you will have this abstract binary, or sorry, this virtual assembly code that's in there. And if you're now running this on a GPU that's a few years in the future, well, it most likely will have a different instruction set. But there still will be a JIT compiler, a just-in-time compiler, that can understand this PTX code and on the fly convert it into the binaries for that particular architecture. So this is how it looked like in the old world, in the pre-CUDA5 world. Now, as I said, the main problem here is that at the time of linking, the host linker doesn't know anymore what to do with this PTX code. For the host linker, it's just data. Now here comes the real confusing rhyme. So what happened now with CUDA5 is that we introduced a device linker. So that means that with this device linker, you can actually look into CUDA code or PTX code or CUBIN code that's sitting inside your object files, link those pieces together, and then hand it off to the host linker that grabs the host pieces of code, and you create the final a.out, the final binary. So long story short, the cool thing here is that this allows you to write libraries of device code, of kernels. Right? And so that's a mechanism that we use for implementing the device callable runtime library, but it also can be a mechanism for whatever, an ISV to write their own whatever secret sauce code, secret sauce library that they then sell to others, and other people can then just use this library and link their GPU code against. Again, if you haven't heard about CUDA before, you may think, well, what's the big deal? I mean, that's what you do on the CPU side all the time. Well, it wasn't possible prior to CUDA5. So that's one of the nice software engineering features that got introduced in CUDA5 to allow you to do true device-side linking. How does it look like in practice? So we have, if you remember this picture here, maybe just a few more words. We have the two source codes, A.cu and B.cu, and we want to link them together. So in the first step, we compile A.cu and B.cu, and what you would do on the CPU side is you would provide the -C flag to tell the compiler it should stop after compilation. Well, we now have the -DC, the device compile only flag, to tell the compiler it should stop after compiling the device code. And so it will produce an A.0, an object file for both host and CPU code of A, and an object file for host and CPU code of B. And so in the second invocation, we now link with the -d link A.0 and B.0 together in this link.o. And finally, we use the host linker, and we link A.0, B.0, and the link.o, which is our GPU library of our linked together GPU code, and we produce a final binary. So just a bit, yeah, that's fairly technical, but that's the way you would use it on the, if you want to use a device code library, or if you want to write your own device code library. Prior to that, just to put it into perspective, prior to that, given that you couldn't build libraries and link them together, you basically had to recompile the entire CUDA application every time you wanted to rebuild, or all the device code. And so that could yield huge amounts of, or cause just huge build times that with this mechanism are cut away now. One small thing here is that linking at the moment happens only at cubean level. So you actually need to target one specific architecture, like we do here with SM35 or SM20. OK, I guess it's close to 3 o'clock now. Where to find additional information? So I'm fully aware it's a lot of material, short time. If you're new to the material, it might be a bit overwhelming. As I said, docs.nvidia.com contains all the knowledge about the GPUs. If you're new to CUDA, I would start with either the best practices guide or the C programming guide. There's a Kepler white paper that describes all the additional features, and I think it's, I don't have it here, but it's also linked from the CUDA website, the docs.nvidia.com. And that's it for now. So if there's any questions, please let me know. Otherwise, I think we are supposed to have either a break or alternatively a tour of the computer room.